Having heard that, I don't know why I'm talking, to be fair. But anyway, nonetheless, GIS, who has used it? Right? Who uses it on a daily basis? Who is a GIS professional? Who uses maps? Sweet. All right, so today, really, I guess my passion is geography and the melding of geography with IT and with data in this modern connected world we live in. So, the flow of today's presentation, a bit of an introduction very quickly to myself. Also, I'm going to dive into the past. You know, where did GIS come from? What was it? Why are we where we are now? The present, what's happening at the moment. This is when I hand off to Santosh and he talks about all that whiz-bang stuff we just mentioned. And then we'll come back to talking a little bit about what's happening now, what we're doing now, and then some predictions, some thoughts about the future and the world we play in. So myself, again, UC, studied geography. I was a kid in bed, mum and dad still talk about it, 3 years old with a big damn atlas apparently. I guess I loved maps, I've always loved maps. So I've followed that passion through. Lived overseas, worked in California with Esri, biggest GIS company in the world. And then, yeah, as of late, crafting up applications in GIS and data solutions in New Zealand for New Zealanders and for our companies. The team, we started early in the year, so February really, we kicked this thing off. And it's going pretty good, pretty fast. So as of November, we'll be 9 people. And we're a mix of data developers, web specialists, all with a bent on geography and a love for maps. Doing some interesting stuff. Saga's recently joined us. He's an AI specialist. So now we're crafting Geospatial and AI together. It's been an interesting few weeks and a big learning curve, especially for Santosh and I. Now, Jon Snow. It all started with Jon Snow. Not this Jon Snow, this Jon Snow. So 1850s. He was an epidemiologist, and really he's the father of epidemiology. He's the guy that worked out that place and space matter. So cholera outbreaks, this is a modern version of the map we're just looking at. Cholera was thought to be airborne. He's the guy that worked out it was through water. So that guy, that thing in the middle is a water pump, the Broad Street water pump. This is 1852, I believe. And really it's the first time that the power of geography was used to affect the whole industry and the outcome and livelihoods of people, and in this case, spatial epidemiology. This is quite close to my heart. My first job was Ministry of Health. So I love the fusion of, I guess, maps, power, geography, data, and health industries. Again, back in the past, this was hand-drawn. Imagine how long that takes to hand-draw that thing. There's telegraph cables back in 1872 by memory. And of course, they were plotted by sextants and all those sort of things using, well, off the boat, right? Stars, all that sort of stuff. Today we take it for granted, GPS, very easy to do this sort of stuff. Both make the map and collect the data. Again, imagine how long that took. This one, turn of the 18th century, this is what Africa looked like. This is when that big yellow bit at the bottom, they used to think there was a huge inland sea there. This is back in the Livingston and Arrowsmith days, I think it was. So again, these were the maps back then. But this is the start and the origin of the modern world in which we make maps. World War I, trench warfare. Maps, the front line, the trenches, obviously the German lines at the top, no man's land. Again, these things were plotted and updated every day by people running through those trenches, through the dugouts, and understanding and planning their next move. How do they get across that no man's land, the barbed wire, and get the Germans in this case? Powerful. Now, GIS as we know it now, I guess the modern origin started in Canada. 1962, Roger Tomlinson started Canterbury GIS system, the CGIS, and it was all about land management. GIS is a term, Geographic Information Systems. The first published recording is in this one on your right, 1965 in a paper. And then this thing here, 1967 came out, which was the land management system, the first true GIS system globally. Now the next thing we're going to look at is a cool little video, 1967 video, and it explains so succinctly why GIS was required in the way in which we think it now. So I'll play that.
To make decisions, we need facts. But we have facts. We have all seen soil maps and census figures. So what's the problem? The problem is not making the surveys. It is trying to read and summarize the results of the surveys. The amount of work involved in handling this data is enormous. Even the simplest operations take hundreds of people. Raw data and statistics have to be cataloged, stored, summarized before the data can be used to make decisions. The process is painfully slow. It's bad enough when you're handling census data. It's even worse when you have to handle maps. And so much of our land information comes only in maps. Suppose an administrator wants to find out how much good farming land in his province is still undeveloped, and where. He has to compare the maps showing good farming areas with the ones showing present land use. But they are not at the same scale. First, one map must be remade as a transparent overlay at the exact scale of the other map. Checked, retouched, positioned. To measure the area where both factors overlap, he will probably use a dot grid, a method that hasn't changed since the days of ancient Egypt. What if he wants to consider other factors, such as the incomes of the people, crop yields in a certain soil, forestry, wildlife, recreation, climate, census data? To compare two factors over 100 square miles will take one man a whole working day. To compare only 6 basic factors for all of Canada would take 556 people 8 hours a day for 3 years. It would cost $8 million. But we don't have the staff, we don't have the time. More resource data comes in every year, every month, every day. Crop and forest assessment, soil surveys, forestry surveys, timber pest counts, wildlife surveys, sampling, analysis, and many others.
So that sums up pretty well, I think, why we needed to invent this thing. And it was at the time, actually, post-war, when people were doing a lot of, especially US Defence Force. That's when the computer generation took off, and Roger up in Canada worked out, hey, we can use these computers to do stuff with this map stuff, all this data. I'm going to flick through this one. Again, 50s, 60s, 4,000 people making maps by hand at the Ordnance Survey of Britain. I mean, huge cartographic divisions. Software, we're running out of time. Santosh.
Thank you, Kurt. So back when those systems were being developed, back in since about the 80s, this is the classic information systems model, right? So this is the classic where you have workers working at the transaction processing systems, middle managers, senior managers, etc. So since the 80s and the 90s, GIS sat there as a decision support system, was used to make decisions. So when I first saw this, it didn't quite fit well with me because I've worked with all the different branches of the organization, from workers to CEOs to executives, and I've done GIS projects in all these different sections. So what is it that a GIS specialist does that goes across these branches? So I went back and started collecting all of my proposals, and I put together kind of a word cloud just to see what is it that I was doing. And I was expecting the word GIS to stand out, right? But to my surprise, it was data. So that's when it hit me, right? Yes, GIS is important, but what's important is the data that drives all of those decision making. So going back to the pyramid, the project I was doing for the transaction processing branch was involving data capture, geospatial data capture. How do we capture geospatial data, and how do we collect it? The practices that are required to accurately collect this data. And for the middle managers, it was managing all the data that's coming in. How do we store it? How do we manage it? Then the level up was data analytics. Is how do you analyze all of the data that's coming in? And finally, for the CEOs, it was the data visualization. How do I visualize all of this data to take action upon these things? So what I'm going to go through is go through each of these branches and kind of explain what a geospatial professional does on a day-to-day basis in all of these different segments. So starting with data capture. Here's a classic example. Here's we have about classic 6-inch imagery, which is about 15 centimeter imagery of a town in Texas. And we have beautiful cadastral parcels that were surveyed in back since the 60s and 70s and the 80s. Now, what is wrong with this picture? It's offset, right? So there's about a 30 feet offset, which is about 15 meters. Now, how do we manage this? How do we deal with this? Now, this is a small town in Texas. You can go in and manually move the parcels and fix them up. But when you're talking about big cities like New York, Dallas, LA, how do we manage and deal with these large data sets? That is the problems that we are challenged with. And so there are several techniques that you can apply. There are several techniques that you can apply to. Okay, that's moving. Okay, you can apply to fix those data sets to see where they are. Now, a 10-meter offset, if you're trying to get somewhere, if you don't know how many people have used Google Maps and put in an address and it gets there, but your house or the place you're trying to get to is still about 10, 15 meters away. That's okay. If you're trying to get there, that's fine. But what about in today's world of autonomous cars, right? If the fire hydrant is 10 meters away, your brand new Tesla is going to be a very expensive paperweight, right? So it's very important that we keep track of all these accuracies in the data and how do we collect them. And the next step is data management. Now there are two kinds of data in geospatial data. So we have static, that's not changing over large intervals, and then we have dynamic data that's constantly changing every minute, every second, every hour of the day. So here are some examples of static data. Satellite imagery, everybody's seen Google Earth. So this is relatively static. It doesn't change as much. But they are huge data sets. These come in terabytes and petabytes worth of information. How do we manage that? Then we have elevation models. These are elevations across the world, the country. These don't change, maybe not so much in Christchurch. They might change due to the earthquakes, but for the most part, elevation doesn't change as much. And then we have high resolution imagery, right? This is going down to 5 centimeters, 2 centimeters resolution of imagery. And these all also massive data sets. Then we have dynamic data. Now, though these might not be big amounts of data, they are constantly coming in at very short intervals, like weather data, for example. This is a wind map done by NOAA. And so that each of those arrows that are pointing is a data that's coming back every second, and you're mapping that. How do we store that? How do we manage that? That's a challenge. Then we have river flow data from ECAN, for example, managing our rivers. These are coming in on a daily basis as well, or on an hourly basis. Road conditions, right? For example, Google Traffic, when you go, it tells you this road is closed, or how do you manage that? All of that stuff. Then we have data analytics. Again, we have two kinds. We have the vector analysis, which looks at the geometries and the attributes and the relationship between them. And then we have raster, which is performed on images. And how do we collect vector data, like points and lines, and how do we convert them into images, useful images? So here's an example, topology. So this is looking at any assets that you might have, roads, utilities, pipelines, any assets where information flows through needs to be topologically correct. They need to be connected at every node so that the flow is maintained. So how do we do that? Then we have classic overlay analysis. So here are the properties around the plenum area. And so it's just plain properties. Now we overlay some orchards on them, and we can now suddenly see where the orchards are with relative to properties. And then now you can overlay the property value. You're beginning to see a pattern emerge here. All your urban properties are a bit more expensive than your rural properties. And then finally, if you turn on the agriculture layer on top of it, you can see that grasslands are not as expensive as some other properties in the area. So you can get some classic real-world analysis using vector data. Then we have Raster Analytics. So here's an example of Raster analysis. So what you're looking at here is the land use data that's coming from Landcare Research, and what they've done is they've taken the Landsat imagery and figured out what kind of land use is going on in each one of those parcels. So clearly you can begin to see between 96 and 01, what is the greatest growing land use in the plenum area. It's mainly orchards, vineyards, and horticultures, and that immediately gives you an idea of what's happening to grasslands and pastures going into vineyards. And then we have points. This could be weather data, could be well data, could be any kind of point features that you can convert into raster surfaces to get a bit more insight as to what's happening with each one of those points. Then finally, we come to data visualization. So this is, again, we have two kinds. We have paper maps, which are the which go into your reports, which go into your articles and documents. They are relatively static, can't change them as much, they are not interactive, and they are pretty hard to replicate. Like Kurt was showing earlier, all those ancient paper maps are really hard to replicate. Then we have dynamic maps and digital maps, which are happening. Everybody has seen it, Google Maps on your phones. Pretty much any app that you pick right now has a mapping component to it, and they're all dynamic. They're putting up their latest data, and they're interactive, and they are pretty easy to replicate because every other app out there is doing it right now. So paper maps, though we can generate these using computers, we still need to have a strong understanding of projections and coordinate systems and how do you interpret paper maps, right? So for example, National Geographic is a great example. They make some amazing looking maps, and they put in a lot of detail on how do you interpret that. What is the scale? What does each point in the location means on a map? And if you look at that, the amount of detail that's gone in there, every town, every village, every river is shown on a paper map. To do that is copious amount of man hours. Finally, we have a digital map here. So this is a classic example. This is just showing what a farmer in King County in Texas, when can he plant cotton, right? So here we are getting data coming in from the National Weather Service that's giving you all your real-time weather forecast data. And then we have local universities providing us with soil sensors, soil temperature data. And then we have the Bureau of Land Management providing the county's data. So how do we overlay all of that, analyze it, and provide a decision-making tool in real time to our farmers, to our producers, to see what is a good time to plant your particular crop. So that's a great example of all of those previous things I talked about: data capture, management, and analytics and presentation. So as a geospatial developer, we need to have an overall understanding of the system. Right? I might be a specialist in analytics, or I might be a specialist in database, but I need to understand how each one of those segments of the pyramid works in order for me to do my job. So the pyramid that we saw earlier looks more like this, right? With data sitting in the heart of it, capture, management, validation, integration, analytics, and precision, driving forth the innovation that's going on. So I went back to my initially did the proposals, and I went back to my RFPs and RFQs and saw what the biggest word was. It was GIS. So what I saw there was all the RFPs and RFQs coming out, they all wanted GIS, but what they were missing was the data aspect of it. So as geospatial developers, we need to keep up with all technology so we can pursue our passion for geography more effectively. And in today's world, with technology ever so growing, we need to keep up and keep learning. That's 2 cents. You could.
Okay. Right, we won't focus on this too much. Lots of commercial vendors, Esri, biggest GIS company in the world. Lots happening in this space. Now, that actually moves. Right, a couple of things we're doing right now. This is a simple map. To us, this is our sort of bread and butter. How do we put points on a map, dynamic map? In this case, how do we show off all of the GPs and pharmacies with the latest data, extract that stuff out of an Excel spreadsheet, visualize it, present it to the audience, and say, hey, this is where this stuff is. The next thing is analytics. So you start to bring in demographics. Where is the population of need? Who is the sickest? Who needs these services, right? This is what the Ministry of Health is very interested in. So again, point, visualization, then expand it with analytics and drive more value out of this data. Routing. Look, IoT, lots of stuff moving around in space. How do we move that stuff around more efficiently? Some stuff we're working on here, building up some interesting routing solutions, to be fair. Again, really interesting work, lots of stuff coming. This is the sort of stuff that drives Uber, that's going to drive all the autonomous car network stuff coming forth. 3D, everyone talks about it. Everyone's talking about BIM. I like to think about GIS as horizontal BIM, right? A BIM is typically a building information management service or whatnot, a modeling service. How do we show horizontal linear assets in 3D? This is LiDAR derived from helicopters. What we're looking at is surveyed plus or minus 3 centimeter space for the towers, for the conductor lines, for the trees and the buildings in that corridor. You can see an interesting cliff. That's where the digital elevation model we're streaming in from Esri, I think in this case, is not up to spec of the local service in data, right? Purely because that's a global service, and in this case we're using very high resolution surveyed LiDAR data. Again, analysis, vegetation management. How do we know and do 3D analytics to automatically generate work orders to send the work crews to the places they need to be before a bigger wind event happens, knocks over a power line? Right? So again, data can drive all this stuff. not just a pretty picture. This is true 3D presentation with analytics that can be driven through it. I like this one here we've done. The old and the new, I like to call it, right? So 1950s and 60s copper telephone cables that have been digitized, and it's not playing for some reason. Can you hit the spacebar or something? Codec unavailable. Okay, well, we'll just move on to this one. Imagine if you can see under the ground. Right, so here we've got, again, utilities. Let's mash up all of the utilities. Let's present them all in one space, and all of a sudden we can start to do before you dig management. We can start to do forward works management. We can start to understand what happens if we're trying to build a 2-meter water main in amongst all these assets down a street, and we have all this data coming out of CAD in this case. This has been geo-referenced into a GIS system, but how accurate is it? Is it actually where it's meant to be? If we dig here, will we hit something even if the map's right? We see this all the time. You present a map, people trust a map. But I know that a lot of that data is QLBD standard, which basically means we don't actually know. We think it's there, right? And that's critical, because if you're going to dig something and hit an 11 kV power line, you're dead. And then capturing information, right? So this 3D model is using photogrammetry solutions and actually technology that's come out of the animation studios like Pixar. And all that is, that took 30 seconds for someone to capture photos. There's about 8 photos, and that's been served up into a server, and we've built a 3D model that drops itself on the map because we have GPS coordinates from the phone, and all of a sudden you've got the information that you don't need to dig to and look up that stuff again, right? And you could go, my asset system, my GIS map doesn't have that orange cable. Something's wrong. You can identify it, you can see it visually, you can go fix it. Where's things going? So GIS, look, we've made maps. It's one of the old. It's a bit old now, I guess. It's 60s. It sort of kicked off. But all the stuff that's affecting lots of IT business and business in general, artificial intelligence, AR, VR, all these technologies, right, are affecting us as well. So what do we do? How do we keep up? We're playing around in the AI space as well as the AR, VR space, right? We have these platforms of data. How do we one day present data in a VR? So you walk, or an AR, walking down the street, you understand what's under the ground, right? People are doing that now, but they're just fancy toys, because no one can tell you and give you certainty on is that pipe actually there? Because if the data's wrong, waste of time, right? So we have to sort the data out first. This last thing, so that harks back to that little video he mentioned. How do we store, manage, and analyze it? Same problem now. 1967, now we have petabytes of data, but it's actually the same issue. Everyone's grappling with it. So it's quite an interesting insight, I thought. 67 to now, we're still grappling with the same problems. We just have way more of this damn stuff. And one last thing, education, right? So I personally, I guess I'm passionate about this stuff, but I want to see a renaissance of geography, right? Bring back geography properly into schools. It's geographic thinking and thought and understanding what place and people and spaces mean, right? Human geography, understanding what it means that we live together, we live in a community, that things are somewhere and things are related to us. Leave you with the last note there. First law of geography, right? Everything is related to everything else, but near things are more related, right? So just think about that. Thank you.